Hi, this video is about sound waves. Sound waves are a mechanical type of wave. They require a medium that can vibrate, a physical medium. They're longitudinal waves. We've talked about those before. And they're created by some type of vibrating system. So like all waves, they transmit energy, but they don't transfer matter. So as you're hearing me, as you're listening to this video, sound waves that are produced by the speaker that you're listening to produces a traveling disturbance that goes through the air, and it reaches your ear, and it causes your eardrum to vibrate, and then that's transmitted eventually to your brain. But the air from the speaker doesn't actually necessarily go into your ear. So as I talk to you in the classroom, the air in my mouth doesn't go into your ear. That's a little gross, but it doesn't do that. But the information, the compressional pulse that starts from the molecules in my mouth that transmit to the molecules in the air, and then the next molecules and so on, and then eventually into the molecules in your ear that are already there. It causes them to vibrate. So the energy is transmitted, but matter itself is not transmitted from one place to the other. So in any case, as the source vibrates, whatever the source of sound is, a series of compressions and rarefactions are produced. So we call the region of high pressure and high density a compression, and the region of low density and low pressure a rarefaction. So that's literally where the air has been made rare or scarce. So be careful on the spelling on that. That's R-A-R-E, faction, F-A-C-T-I-O-N. So I've sort of tried to draw that graphically for you on the next board here. So this is a compression and then a rarefaction, a compression, a rarefaction, a compression, and a rarefaction. And again, compressions are high density, high pressure, rarefactions are low density and low pressure. So when something vibrates, like I have a tuning fork here, when this fork vibrates, it literally pushes the air and creates a compression, and as it pulls back, it stretches the air out and makes a rarefaction. So sound waves travel in gases and solids and in liquids. And in general, they travel faster in solids than liquids, and faster in liquids than in gases. So if you've ever heard someone produce a sound while you're maybe swimming underwater, it sounds very different than it does if you hear the sound in the air. Or perhaps you've laid your head down on your desk before, and sounds sound different coming through the solid surface of the desk than they do through the air. But generally, sound waves travel faster in solids than gases or liquids. And that's because the molecules are already closer together, and it doesn't take very much to push them a little bit closer together. They're already pretty dense in those materials. Now the speed of sound, in addition to depending on the material itself, is dependent on the temperature of the material. So in air, the speed of sound depends on the pressure in the air. So as you go higher up into the atmosphere has a lower pressure, and the speed of sound would be smaller. Down here where we live at normal atmospheric pressure, we call that 1 atm, 1 atmosphere. And at a typical temperature of around 20 degrees Celsius, that's like room temperature, sound travels at about 343 meters per second. And that, remember, is about, if you double that, it's about 700 miles an hour. So pretty fast, 343 meters per second. And it would be even faster if it were warmer. If the air molecules are already moving quickly because they're hot or they're warm, then they transfer that energy to the next molecule faster because they're already moving faster. So if the temperature goes up, the speed of sound goes up, and if the temperature goes down, the speed of sound goes down as well. But this is a good number to put on your cards, on your toolboxes. It's a number we'll use over and over and over again. So unless you're told otherwise, we'll assume that the speed of sound in air at 1 atmosphere at normal room temperature is 343 meters per second. Now sometimes you'll be given a question where they tell you the speed of sound, or you have to calculate the speed of sound, and it will be close to this, but maybe not exactly that. How do we perceive sound? Well, we can hear, as human beings, frequencies in the range of 20 hertz to 20,000 hertz. So 20 hertz is a pretty low, deep bass sound, and there are animals that can hear below 20 hertz. For example, elephants can. And perhaps you could feel a vibration of lower frequency than 20 hertz, but your ear can't perceive that. And then we can hear all the way up to 20,000 hertz. And again, there are animals that can hear above 20,000 hertz. Bats come to mind, dogs can hear above 20,000 hertz. But our normal range for a young, healthy person is 20 to 20,000 hertz. Now, as you get older, your membrane in your eardrum gets a little stiffer. It loses some elasticity, and so you tend to lose this upper end of the hearing range as you get older. That's a normal part of aging. If a sound wave is below 20 hertz, it's called infrasonic. Infra means below. And if it's above 20,000 hertz, it's called ultrasonic. Ultra means above. And as I've indicated before, that frequency is correlated with pitch or note. So I have two tuning forks here, and I have no idea if this is going to catch on the camera, but I'll try it. I'm going to strike this one. This is middle C, 256 hertz. So when I strike this, it vibrates back and forth 256 times per second. I'll hold it close to the camera. We'll see if that picks up on the video. We'll hear it in class if it doesn't. And this one is 512 hertz. This is an octave above middle C, so it should be higher pitched. Maybe you can hear that on the camera. If not, we'll hear it in the classroom. So frequency is correlated with pitch, or the note. Loudness of the sound is correlated with the amplitude. So sound waves that have large amplitudes, that is high compressions, high pressure regions, and very low pressure regions, they are perceived as loud to us in sound. So I think armed with that knowledge, we can go on and do some things with sound. Thanks.